It's my pleasure to introduce Gianni Antichi. He comes to us from technically Cambridge, but
I'm going to turn off the ATM audio because there's nobody there.
okay.
So, you go ahead.
All right. So he comes to us from Cambridge, technically Queen Mary University. He does a lot of work at the intersection of systems and networking, software and hardware. He focuses on designing monitoring frameworks, algorithms, trying to find ways to efficiently embed them in hardware. The most interesting thing about him is that he has a cat that's very, very cute. And if we're lucky, it will show up in the background during this talk. And he's been doing a lot of interesting work in the context of programmable data planes and eBPF. And today he'll talk to us about some of the work in the programmable data plane space. And with that, I'll hand it over to Gianni.
Thank you, Theo, for the introduction. Also, thank you for pronouncing my surname correctly. I think this is one of the first time that someone that is not from Italy managed to pronounce my surname correctly. So that's that's pretty good. And yeah, my cat has already eaten, so it's like the probability that we show up is gonna be like way less. But we'll see. Anyway, thanks again. It's really a pleasure for me to be here. And today I want to talk a bit on some of the work that me, my group, and collaborators have been doing in a context of how to rethink network telemetry now that you have programmability in the data plane. And just to provide a little bit of context, if you think about it, it has really brought fresh ingredients to researcher. And if you think about even past research in the last top conferences, you have seen like a lot of work on cool ideas on how to rethink programmable switches, for example, to act as a key value store in network, or how to do some sort of a coordination, or how to do like a machine learning inference. So this is like a pretty ripe topic for researcher. But it's not just about researcher. If you look into, for example, an interesting paper in NSDI 2018, there was Microsoft showing that they are like putting the SmartNICs in the cloud, and also there was another interesting paper same year in a SIGCOMM. And actually it was a year afterwards, but it doesn't matter, where they were showing how they could do like in a combination of using programmable switches and some telemetry, how they can do like a really congestion control that can work like really greatly. So, anyway, so lots of application, but maybe it's me that I'm kind of biased, but every time you think really about a killer application for programmable data plane, it's like the things that comes into mind is really INT, which is the in-band network telemetry. And for those of you that never heard or don't know like really what's INT, is basically, the idea is pretty simple. The idea of INT is you have a packet that is flying over your network, and you can add some information inside the packet. And those are telemetry information that they can be collected then at the end of the life of the packet. And those information can be something like, switch ID, egress port ID, queue occupancy. And so those information might help you really to understand what is going on in your network. So just to give you like a sort of an idea really how INT works, you have a packet that starts from a TX and has to go towards an RX and a receiving. And it hits the first switch had some information, the second switch had some information, then this packet arrived. So really, INT is a super powerful tool that helps you to answer a question like, is there a congestion a queue build up in my network? And then of course you can use that to refine your congestion control properties, which is what the Alibaba work was doing basically. Or you can understand if your routing paths agree with the policies that you wanted. Or for example, if you have like load imbalance in your network, basically because when you send a packet, you embed the metadata value, you ask some information, and then effectively all the switches embed those information. So, and indeed, because this is very powerful, INT is deployed in major companies, but also has been used in a number of contexts. congestion control, as I discussed before, but there was also another paper interesting in Connex 2017, where they were showing how you can do load balancing within the data center network. By leveraging INT, you could understand effectively what was the status of your network, and you could load balance your flows in a way that you could have like a good utilization overall. But also like a pretty interesting use case for INT is path tracing, which is effectively understanding what was the path of your packet. Now, what's the problem here with INT is INT effectively is expensive. And when I'm talking about expensive, I'm talking about really the overheads that INT introduce in your packets. So if you look at what INT requires requires an 8-byte header, which is the header that the source used to instruct the switches along the path to ask, oh, can you add, information X, Y, Z, and then each information is encoded as a 4-byte numbers. So effectively, what is happening here is that if you think about how was the life without INT, a sender would have sent a packet with a given payload. Now, if you have INT, you need, since the MTU of the packet is still the same, you can send less payload because you need to embed, the INT. And this is the cost somehow of the fact that you can have more visibility in your network. So the other problem is definitely like this cost of the source to prevent the number of towards the destination and leave space for telemetry value. So because you want to avoid anyway fragmentation and stuff. Now, we try to understand really if this was a problem. And in a paper that we presented last year in SICAM, we try first to understand what was the cost of this overhead. So we started a little bit by doing like some simulation. And in this simulation, we effectively took like a fat tree topology, pretty standard fat tree topology with 5 hops, ECMP load balancing, and we try to reproduce a traffic with characteristic of following characteristic of data center networks. There are plenty of papers that they provide, sort of CDFs of flows like web search and data mining. And we try to understand what was, what would have happened to the flow, or specifically to, as you can see here from the flow completion time, when you, increase the overheads on the packet. And we tested it with a different like load utilization of the network, like 30% or 70%, just to have like a sort of an idea here of what would have happened. And what we realized is like we could have, of course, this is like highly dependent on the overheads, and so the amount of information you ask from INT. But what our main takeaway was that we could have almost 25% increase in flow completion time, which is not definitely what you really seek to have in your network. Although this is, again, you might argue this is the cost of the visibility that you might have. If we looked also at the normalized good put only for long flow, and we realized that even in this case, we figured out that there was almost 20% degradation in good put. Now you might wonder.
Before you move on, can I ask a quick question?
Yeah.
Why is this overhead dependent on network load? Especially if you go back to the previous slide where you had the normalized FCT, right? You found that sometimes at higher load, at higher load at the same overhead, the normalized FCT is lower, and sometimes it's higher. So particularly the strike bar for 28 bytes of overhead, actually 70% load there is better, and then at 108 bytes it's worse. I'm curious why that happens. That's my intuition.
Now, we investigated a little bit, and we did like we tried to get an average, but the conclusion was this is more an effect of ECMP load balancing. Sometimes you are like quite unlucky. Sometimes you are a little bit more lucky, and you get some, results that they are not really the way that, you might get more lucky or unlucky, and the flows that you get flow collision, and then you get, flow completion time that increase just because, the hash is triggered you to go and have a multiple flow on the same path. We decided to include anyway results for 30 and 70 because we wanted to show you that anyway, this is like a pretty consistent. If you look at on an average, you see that this is a pretty consistent behavior, but there are like some cases, as you mentioned, and this is mainly due to ECMP.
Okay, so the takeaway from these two graphs should be, on average, there's an increase, but we shouldn't so much focus on the particular parts.
Yeah.
Okay.
Yeah, exactly. And I think another important takeaway is if you think about overheads, those overheads that we try to use are not that completely unreasonable. Because if you consider a 5 hops fat-free topology, a 28 bytes overhead on packet would be the cost of just doing path tracing with INT. So asking every switch to embed the switch ID so that you can get an idea of what was the path of your packet. Or for example, HPCC, the congestion control from Alibaba, impose an overhead of 68 bytes. And of course, if you want to have multiple type of queries at the same time. So for example, you want to do HPCC, so you want to have INT that hides your congestion control, but also does path tracing, then you get, an increased overheads. So I guess, the other thing here is important is those numbers, although they might sound high, like, okay, whoa, 68 bytes overhead, these are, they are kind of reasonable and they might happen in a context of 5 hops topology. So then, in this paper, when we realize this, we start, asking ourselves a simple question like, can we do better? And, the simple answer to a simple question was, well, if we want to use bits on packets, less bits on packets, you have less, you have less problem that you saw before. Now, here the insight that where we start is most of the time collecting all per packet and per hops value can be highly redundant. That's the insight where we start really this work. And today, mainly because of amount of time and because I wanted to discuss also other things, I'm gonna show you just one example, which is the one of a path tracing. In the paper that we presented last year, we show also other examples related to congestion control and also to latency calculation. But I'm super happy to discuss also the other example if you are really super curious. But because of the time, I just decided to pick just one, just to give you like a feeling on how this would work. So this way I could stay like within the time. The insight here is that, okay, we want to perform path tracing. So we want to collect the switch ID. And, the thing here, the insight is we should spread the information over multiple packets. So what does it mean here? Now, let's return back again on how INT will perform path tracing. INT will perform path tracing by, a packet is flying around the network, it will hit the first switch that will embed the switch ID, then the second switch will embed another switch ID, and third switch will embed the third switch ID, and so forth. And effectively, when the packet arrives, you will know at the destination that the packet hit A, B, and C. And then another packet belonging to the same flow, you will get A, B, and C, and then A, B, and C, A, B, and C. This is a case where we have like a sort of a path to flow consistency here. So effectively here is a kind of, if you think about it, somewhat is also redundant a little bit. So then our idea was, okay, why, and I recollect back to the slide that I said before, why we don't spread this information among different packets. So basically, what if the first packet just send, A, the second packet maybe A again, the third packet C, the fourth packet B, and then so overall, what's the path of your packets. Of course, this is easy to say, but then, it comes with a few challenges that you need to think about. And basically the 3 challenges are like, first of all, how switches can independently select if they should store the information or not in the packet, or how to converge as soon as possible means, we want to reduce as much as possible the number of packets that you need to really understand what was the flow, the path of your flow. But also, what if we require even less bit per packet than the actual switch ID? How can we handle that? Now let's start with the first one. And yeah.
Why not use MPLS-like approach when basically you have At every switch, you change the level and it identifies the path until that switch.
Because effectively here we wanted to take INT approach because we wanted to be a little bit more generic and trying to show that we can find, let's say, a way to reduce the overheads on packet to take all the information that INT will provide. Now, I'm providing you just one use cases, one example on how this system will work for specific for path tracing, but there are also other measurement values that you might want to collect if we want it to be like a consistent with INT, if it makes sense.
Sounds good. Sounds good, is what Michael said.
Okay, so sorry. So the first question here was how switches can independently select if they should store the information or not in the packet. So if you think about it, if you know in advance what's the path length, it's kind of easy because, you know, if the path is k hops, you could have every switch embed its information with a 1 divided by k probability, more or less. The problem is, what about if you don't know the path length in advance? And here where the first bit of theory came in our help, and there was, you know, this technique that is called reservoir sampling, where reservoir sampling is a family of randomized algorithm for choosing a random sample from a population unknown set. And because I'm super strong in math and I'm more a system person, I'm gonna give you like this, what does it mean effectively? This means that if you wanna have a same probability for an unknown population, you need to pick the height element to be chosen with probability 1 divided by I. That's really the takeaway for like mostly system person here. And our hint was, hey, we can do that by using the TTL of the packet. What does it mean that? Let me just give like a sort of example here. So we have a packet that starts from a source, and this packet has an ID. Now, ID can be whatever you want. There are like plenty of papers in the literature that they show how you should pick a good ID for a packet. Some papers advocate for IP flags, IP offset, a TCP sequence. So this is really beyond the specific of this algorithm. So let's assume that the packet has an ID. And the packet at the beginning has a TTL 256. Now, let's assume that here we have a first switch that has that calculates an hash function that depends on a k, so the ID of the packet and TTL, and returns a value that is between a 0 and 1. So what we do here is that we add information inside the packet only if this hash function returns a value that is less than 1 divided 256 minus TTL. Why we do that? We do that because we arrive at the first hop, and 1 divided 256 minus TTL that now is 255 is going to be 1. Since we said that this hash function is going to be between a 0 and 1, you know, you will always add the information at the first hop. But then you will arrive at the second hop. And the second hop, you add the information with probability 1 divided by 2. And then you will arrive at and let's assume that this is not the case. We arrive at the third hop, and we just following again the question, you will add the information if you have a value that is less than 1 divided by 3. So effectively, we implement a sort of what I was telling before. And in this case, let's assume that we add the information. So effectively, this is we created the first mechanic, and I'm gonna refine it in the next slides. So bear with me a little bit with that, to kind of assemble like a switch in a way that doesn't need the really coordination between switches. The problem that then we faced was, okay, now that we have those numbers, how can we converge as soon as possible? And the reason why how we can converge as soon as possible is that because when we realized about this, we were all happy. But then we realized also that if you just record the switch ID, it's really fast to get the first numbers. But then latest one requires a high number of packets because you might have like a long tail. in a sense that, you know, you might get lucky. At the beginning, you don't know any numbers, you don't know any of switch IDs, so whatever you sample, you're perfectly happy to. But then after a while, you know, you need to get lucky to get, you know, the real switch ID. I know you can kind of infer the switch ID based on what you get, so you know more or less your network topology. But we wanted to be really thorough and try to see, can we get all the numbers, or so how this will work. And we, you know, and these things created a kind of a big tail. So then we start asking ourselves, okay, so wait a second.
Gianni, before you move on,
yeah.
Can I ask a quick question?
Sure.
So it seems to me like you're navigating a trade-off space here, right? Like this probabilistic scheme is very clever, but the underlying assumption is that, you know, paths tend to be not super duper long, right? If your path is less than 10 hops, then, you know, at the last hop, at the 10th hop, you would have a 10% probability of adding the switch ID. So that's pretty good. You don't need that many packets until you actually get a full trace of the path, right? But if your path was 500 nodes long, then, you know, of course, you need a lot more packets, right? And there seem to be sort of, you know, some built-in assumptions here that, you know, most paths are not super long, and maybe most flows are not super big in terms of the number of packets, right? Because if the flow is huge, then it doesn't matter how long the path is. You're going to get enough packets to get the information. If the flow is small, then you've got to be a bit more careful, but it probably will still work well for most common paths, which are probably, you know, only a few tens of hops long, right?
I guess this is spot on and is a part of the discussion that we also put in the paper, which is really about the trade-offs. Yeah, completely right here.
Okay, great, thank you.
Also, since stable paths, if you have links that are flapping.
Sorry, did this one I didn't hear.
Yeah, it also assumes that the paths are stable. If you have flapping links.
So this is another good question that we discussed a little bit in the paper. It's correct. Here we start from the assumption that the path is kind of stable. Let's say that the good aspect here is that if you start having flapping links, then you might realize, because you might get results that they are inconsistent each other, and then you realize that there is something that is happening with your flow. So that if you have a long enough, you know, trail of packets, then you might even figure it out what are the various paths that you might get, if it makes sense.
Yeah.
Okay, so as I was saying, like here, it's really fast to get the first number, but then later one where like we experience a long tail, then we start thinking about, okay, wait a second, what if instead of recording the switch ID, we just record the XOR of multiple switches, you know? And why this might work is because, you know, effectively, if you have, for example, we base on a basic, you know, really characteristic of XOR, and let's assume you have A XOR C, and then you have just C. Then if you do A XOR C, you get A. So from XORs, you can kind of infer this. So we thought like, hey, maybe this is like, you know, if we do XOR, this is gonna be even faster. We were unlucky, it didn't happen. And it didn't happen because basically, to make this work, actually, you need to be also lucky to get some C, just single numbers, and then you can start inferring the things. So basically, just to cut it a little bit, what we realize is that an hybrid type of solution was the best. And a hybrid type of solution was you start by just having, you know, your baseline. So the first things that I told you, so you just pick a single like labels. And then after like a little bit, you switch to XOR, or you know, enforce a probability in which you switch to XORing. Because if you do like this, once you have already just you know, a good number of single switch IDs, then you know, you get it like it's faster for you to get to decode all the other numbers. So that's why we decided to use this hybrid approach.
I'm a bit confused about the XOR,
yeah.
What that does. So can you go back to the example? So the situation where you have A, XOR, C, XOR, C, of course you get A back out, but that would require your packet to flow through the same switch twice, right?
No, I'm talking about this is multiple packets, right? So
this
you have
multiple packets, I see.
Yeah. So you get, maybe you see here, maybe you have the first packet that provides A, XOR, C, then you have a second packet that provides you just B, and then the third packet that provides you just C, and then you can infer A, because you can do A, XOR, C, XOR C again, that you have it, and then you can infer A. That was our insight.
I think I'm struggling with the notation of the figures here. So the right-hand figure that you just sort of picked apart, there are 4 different packets in the right-hand figure, right? A XOR C, just B, just C, and B XOR A. And then over some number of packets, some window of packets, you XOR them all together to extract additional information. Is that correct?
Yeah, I could have made it clear, but that's correct.
How do you think that window? Is that just like a fixed number of packets, or how do you XOR all the packets together that you've received so far? Yeah,
the idea was so as long as you get packets, you figure it out if this was a switch ID or it was XOR of others, and then from there you start building. Every time a new packet arrives, check if this was carrying a number that could have been helpful to decode other switches or not. That was more or less our insight. So we were doing like a packet by packet base as soon as we were receiving a new packet with new information.
Right.
Could I ask a question as well? So right now, thus far, when we've been talking about this sort of telemetry, we've been sending individual switch IDs across over, but how does this preserve the ordering information? Like, how do you know A was hit before B before C? Right now, it seems like you only get you only see the which switches were involved, but not which switches came before or after. Even without the XOR-based path tracing. So how do you restore the ordering information?
So we started from the point that the ordering for us was not really super important, because we considered a data center network where you have a full visibility, in the sense that what's your network, what are the IDs of your switches. So effectively let's say where, I don't know, ID 3 is located and where ID 5 is located. So if you just decode that the packet that went through 3, 5, and 6, already if first was 3 or 5 or 6.
But if you have a mesh network in your data centers, this wouldn't work, right?
No, that's correct. This is we did it mostly for FAT3 type of topologies.
Okay.
Just one more question, actually.
Yeah, sure.
So could I ask, how do you decide the distribution of your XORs? So how do you know, say, a packet will have XOR like 2 switches, or like XOR 1 switch, or XOR 3 switch IDs? How do you decide this distribution for the probability?
So that was based on this specific hash function. So if you remember before, I was telling a switch, sample a packet. If this characteristic of the hash function is respected, right? So and before, the idea was in this case, A sample the packet, so A embed its information, B doesn't, C does, and so he just overwrites the value of A, just put his own value C. Now with XOR, effectively what you do is C will not just override the packet with his own switch ID, but it will just do, okay, yeah, I just read the value and I just XOR with my switch ID and I just put the information and I just send the packet out.
I see. Thank you.
Welcome. So then, okay, so let's assume now we get a feeling on how to sample packets, how to try really what's really the trade-off on convergence. But then, we start thinking about, okay, so wait a second. what if I wanna even use on the packet less bit than the actually switch ID requires? Let's assume switch ID, I don't know, requires 16 bits. And what if I just want 2 bits, for example, and I want to just have that overheads on my packet? I don't want more. So our insight was, okay, so you know what we can do? We can store in the packet a hash of the ID of the packet and the switch ID. But this, like, you know, if you store an hash, you can create an hash that returns you a value that is 1 bit, 2 bits, 3 bits. So at that point, you have the flexibility that you want, but then introduce you a further challenge here. And the further challenge is that now you get at the destination a number, for example, 0x101, which does not reflect any switch ID that it was before. Then, you know, it starts like, okay, so now that I have the 0x101, which might be related to many switches around, how really I can decode this? How can I really figure it out that? Now, our insight is the G function, and the G hash function is the one, just to remind you, the one that helps you, the switch, to understand if he has to embed the information. And the H function, which is the one that encodes this number in a smaller number of bits, are globally known. So if you know those functions, then what is happening here? You know everything effectively. You know that because Rx now can kind of backtrack who sampled the packets. Why you can backtrack? Because let's assume that now Rx receive a packet. This packet has the K, so the ID number. Now, since it has the K and knows, you know, the TTL are numbers, then it can kind of backtrack and understand who sampled the packet. So can figure it out, for example, okay, so because of this is the ID, and the G function is the function that all the switches use, is the same function, and I know this function, then, for example, in this case, I know that the D and C couldn't by any means sample the packet, but actually, like, B sampled the packet. Now, this means that effectively the information is Rx can start thinking about, oh, so this information comes, I don't know exactly what was the switch, but I know that it was 2 hops away from me. And I know that given the K, which I know the packet, and the switch ID, which I don't know yet, the hash function, that hash function that I know, return as a value 0x101. So effectively, you start getting enough information to kind of backtrack what was this. And of course, this is yet a huge trade-off, right? So because if you ask like to get only 2 bits every packet, then you will need a lot of packets to try to do this decoding, because it is going to be too expensive. If you ask if you are allowed for a little bit more overheads on packets, of course, you know, you can be faster in this decoding. And this is one of the overheads, one of the trade-offs that we have. Basically, just to give you some ideas on how this worked, is that on a fat tree topology with 5 hops, so not really a lot of hops. We are not talking about really maybe ISP. We are talking about, you know, data center type of scenario where you have a restricted amount of hops. If you are happy to have 1 bit per packet, which if you think about it, just 1 bit per packet will not affect any way potentially your flow completion time. You need an average of 40 packets to, let's say, backtrack of what was the path of the packet. Again, if the flow is a super short, then it might not be helpful. If the flow is long and you have enough packets, this can help. And again, this is a part of the trade-offs of what we try to explore in this paper, right? So try to understand really what was let's say, the design space to get, let's say, embed the network telemetry that kind of requires less overheads on the data plane, because this will allow you to, you know, to have a faster flow completion time. But when we designed that,
can I just ask about the decoding? Because I think that either I missed something or maybe I'm sort of puzzling things together in my head. Sure. On the previous slide, you had this, you know, H of K, switch ID, you know, gives you some hexadecimal number. maybe that's
Yeah.
a binary number, but that's beside the point. My point is presumably your decoding theory here is that you could brute force this, right? You know all the switches that are 2 hops away from you because you know the topology.
Yeah.
You have their switch IDs, and you can just try the hash function on all of them, and if you get a match, then that's where the packet went through. Now, the reason why fewer or more bits matter here is because the fewer bits you have, the more hash collisions you're going to get.
Yeah.
Right? So if I have 100 2-hop switches and only 2 bits, right, I'm going to get a hell of a lot of collisions.
Yeah.
If I have 100 bits, that's a lot of bits, so the likelihood of a collision is lower.
Yeah.
So the trade-off here is if you use more bits, then you don't get as many collisions, but you still have to do this brute forcing at the end, right? Like you have to there has to be some computation to figure out the switch that tries lots of combinations. So do you imagine that this sort of brute forcing is something that happens all the time, or that only happens when you do diagnostics? Because it could be expensive, right?
It could be expensive, and this might create a lot of let's say pressure on a kind of a collectors, if you see what I mean, because you get like a lot of data. Because now before, maybe with INT you will get just a single packet with all the path, and potentially if you want to send it to a collector, you send it to a collector. Now you need to get a lot of packets, and that's partially what I was going to say now here. If you think about this design dimension, call it pressure on collector, but call it also somehow also, as you mentioned, the amount of processing that requires. It's kind of it's a completely opposite of what INT somehow was providing, right? So have with a mind, you have a very, very low overheads on packets, so you can have like a good flow completion time. But on the other hand, you have like a very, very, let's say, high pressure on collector of processing that you require. And that's why I think and this is where I'm heading, in the last part of the talk here. It's like where we wish really to go is like something that is an optimal solution that is more for in the middle between Pint and INT, and that's where a paper that we are going to present this year in Hotnets, I think, is heading into. But before going into that, I want to really just stress why this pressure on collector is quite important to consider. It's quite important because if you look at recent papers from, for example, in SIGCOMM, there was an interesting paper from Alibaba showing what was really, how big was their data center network and how much the collection was really costly for them, because effectively a data center network can comprise of 100,000 of switches. And also there was this paper, as I mentioned, that where Alibaba was saying that every switch might even produce a few million telemetry reports per second. And if you think about in the context of Find, this would have been even more, right? Now, if you think about it, every telemetry report is somehow a packet. So think about it as a packet problem, a packet IO problem. It's easy somehow to saturate the CPU resources of collector. And you might argue, we can use more CPU cores. The problem is, and that, and a takeaway here is really is that managing incoming reports is expensive. But actually, it's even worse than that. When we realize that, of course, a report arrived to a collector, and the collector needs to store this report somehow in a data structure. Okay. Now you can use a naive type of approach, like Kafka. But we also took, like, there was a paper in NNTI a couple of years ago where they provided a very specialized stack for network collectors. So this paper was Confluent, was a paper from guys at Cornell, and they produced this very interesting paper based on the PDK where they're showing, like, look, we can have a really high performance. Now, the takeaway here for us is IO is definitely important, But like actually lots of CPU cycles are spent in storing incoming data in a queryable data structure, because a report arrives, but then you need to put it in a data structure that somehow then allows you to then query back, because that's the point of having a collector where you have your all of your information structure in a way that you can really then query. And then our question was, okay, if this is like really a big problem and it costs a lot of CPU cycles, can switches really insert the queryable telemetry data into collector's memory entirely bypassing CPU? That was our first starting point and question. And the insight here is there is a technique that is pretty well known in the HPC world, but also now pretty well known even in data center normal network system community, which is RDMA, that allows you to write data in memory bypassing CPUs. So it's challenging though. It's not just about, you are gonna craft a packet, an RDMA packet in your switch and you just send it. Because then it opens up a Pandora box of challenges, research question. We don't answer really all of them in this paper. It's more about it's an hotness paper, right? So, but effectively, you start asking, okay, so if you can do that, supposedly you can do that, how to write data which is then easily queryable? Because it's not just about I have some data, I craft an RDMA packet and I write it somewhere in memory. I need then, I'm gonna write multiple reports. How can I write it in a structured way, those reports? But also how to optimize the data organization in collector's memory. What I mean with that, let's assume you have a collectors that receive data from 10 different switches. Now, naively, you can think about, what, I take the memory of the collector and I divide it in 10 parts on part. But this is not really, we didn't think this was really optimal, because there might be some switches that might create more reports, some others less reports. So effectively, it was not really a good idea to us as an exploring now factor, like really considering like dividing in a hardcore way the memory. But also how to make the system robust to telemetry report losses in some sense. So we ended up, this is like a sketch of a system. And of course, again, let me stress that this is an hotness paper. So I'm super happy also to take questions, but I have also myself a lot of questions and few answers, but a lot of questions. And the idea here was, you have a switch. A switch can use a global hash function for a stateless mapping of telemetry key and memory. So effectively, you have a switch that has a telemetry key. I don't really mind at this point what type of information it is. For me, it's a key, is a value that I want to write in my collector. And I use an hash function to map these to a memory, to a place in the memory in the collector. Now, I can then, what I can do is I can trigger a telemetry report from a switch as a one-side RDMA write. And what I can do, since all the switches might share the memory in the collector, what I can do, instead of just writing in one place of a memory, I might just write in n place of a memory. I just create a sort of a sketch somehow, kind of data structure in the collector, and then this means that for every report that I want to send, I need to trigger n RDMA write to resolve collision. Now, of course, this is like open up sort of, we show in the paper that this is actually kind of makes sense with simulation. We didn't implement it yet, and we are working towards implementing that. But actually, while we were working on this, we also thought that this a sort of idea of doing this open up new opportunities to explore. For example, at the moment, we discuss only, or I talk about just RDMA write. But actually, RDMA provides other primitives like fetch and add. And this might be an interesting primitive for in-memory collectors flow counters to have a flow counters in memory collectors instead of keeping in the switch. Or maybe compare and swap, where you can maybe use a more complex storage methods. So actually what we are looking now in the direction is really, okay, so RDMA write is one primitive. Maybe we can also leverage other RDMA primitive to try to do more complex operation that they might help for telemetry collection. But even more, going forward, it might be super interesting for building new direct telemetry access protocol. Because effectively, now that you have a smart NIC, if you think about it for an RDMA, for a smart NIC perspective as a DMA from the NIC itself, from the hardware to the memory of the host. So effectively, you can even potentially, if you can start, if you open up the possibility of having also smart NIC, then you can think about, okay, so the switch might create a different RDMA protocol, maybe a protocol, an RDMA protocol that is just in one packet is already asked to write in an memory location of the packet of the memory of the controller, things that you can't do with standard RDMA. And this way it allows you to start creating like a sort of a transport protocol in some sense for network telemetry. And this is one of the direction that actually we are looking into at the moment. And this is a kind of a big open question, and one of the paths that me, my collaborators, and group are exploring at the moment. I wanna just conclude by just giving a hint on something else that I'm lately thinking about, which is I think is all related to that. Which is effectively to think there is a really growing interest towards implementing concurrent function in programmable networks. There are like a lot of people thinking about, oh, you can do key value store, you can do telemetry. But the problem is like, it's gonna be a challenge really how to fit as many functions as possible. And why you wanna do that is because you might have cloud providers offering network programmability as a service. You might have operators that just want to make the most of their device. And a posting side that might not need function available at any time. And for example, you might have a monitoring specific primitive that you really wanted to load in your switch only when it's really needed because you realize that something is wrong and you want that specific function to be loaded. And if you think about it, then this means that potentially this might open up a sort of a direction towards just-in-time hardware pipelines. And this is not something that I come, it's just me now talking about that. But there is going to be some work to appear in Hotnets 2021 this year that I saw they have that flavor in mind. What I want to really discuss in the last few slides here is more about what if instead of thinking about that, instead of can we apply just-in-time optimization of programs at runtime on the switches? I'm gonna give you an idea why I think this makes sense. So first of all, if you think about a P4 program, this has a fixed number of stages. Each stage has a fixed amount of resources. And it is possible to do multiple lookup on the same stages, provided that there is no dependency. So what does it mean with that is, this is two examples. Think about you have, for example, a match one, so packet header on field and produce an action that is, for example, drop. And then you have another field that match, but produce a similar action, which is, again, that act on metadata drop. So those, since they act on the same variable, the compiler would place these into different stages because this is not possible to write at the same stage on the same variable. And this might be a case, for example, if you have an ACL table for IPv4, one for IPv6, one for L2, and then this means that potentially those would be places in different in different stages of your switch. But it might be the case that, for example, you have a match on a field one. This creates a metadata, and this metadata then is used as a match on the next table. And again, those two actions will be placed in two different stages because there is dependency. And this might be the case of a virtual function where potentially, what if you have just one, then at runtime, one entity installed. So basically where I'm heading into is there are like a lot of optimization that would be that you could do potentially if you know the status of your system at runtime. Example coming back here, for example, you might use, if you create a P4 program that has IPv4, IPv6, L2, ACL possibility, this will put it, will consume three stages. But then suddenly you don't insert any rule for IPv6 ACL. Then the table is unused and you don't have really dependency there. You don't have it at runtime dependency. And you can use it as a mechanic to kind of optimize the pipeline. So question that I have open here is really when to apply the optimization, how to guarantee isolation for components if we swap pipelines between the optimized version and a non, and how to trace before program execution to understand what is happening. We have some ideas in mind on how to do that, but this is even in a more, let's say, early stage that they want to hotnets. I just went through some paper published in top conference, then a workshop paper, and then here is a more like really thinking loud with you guys. And basically what we would like to explore is to have ways to do like a sort of a virtual pipeline inside, and then having the switch CPU that has this just-in-time compiler that can understand if based on the runtime configuration of the switch, you can save switch resources and then recompile the configuration of the switch and push back the new configuration on the switch at runtime. That's all. I know that this is so the last bit is really super high level, but it was more about really ideas that are in mind. I want to really thank the various co-authors for some of the ideas that there were. And since Kat didn't show up, this is the Kat, very interesting. Thank you so much.
So I have one philosophical question.
Yeah.
Telemetry, one of the big use cases is for diagnosing problems. And problems are by definition not normal. They're like statistical anomalies. So the first perfect time for you kind of building on this notion of redundancy is at odds with statistical anomalies. Have you guys started looking into ways to extend time to kind of address or to capture higher resolution data for diagnostic purposes?
So since I heard, let's say 50% of of your words, but let me try to rework your question. The question basically was about you might really not know exactly what you want to query. Because this is something like sometimes it's hard to understand what is going on and how to do that in the context of the hotnets papers idea of RDMA. Is that correct?
No, it's in the context of time. You don't know what a problem is, and you need to get all the data, not just the normal data, but the abnormal data to figure out what the abnormal is. And this is kind of related to what Michael pointed out with the link swapping, but a more general version of that question. So far we focused mainly on trying to, let's say, capture or get the maximum things that you can get. And the reason why is basically because talking with operators, that was their first concern, which was really, we try to capture everything and then we will figure it out, later what we can do. And this is not a super potentially optimal way of doing things, but I guess this is the first step. Understanding what is wrong, it's potentially the next steps, but it comes. I do see these. You can do that, but first you need to find good ways on capturing really all the data.
But
without that,
building off Theo's question, it seems like the whole design, is effectively a sampling design that you pitched, right? In the first part of the talk. And if you sample, you're unlikely to capture rare events, right? Simply because of the nature of statistical sampling. Therefore, this would not be a great tool at finding out rare events in your network, right? It will be very good at giving you common case behavior, but presumably finding rare events would be challenging, or at least require a lot of packets to get, right?
Yeah. I do agree. I think this is matter mostly of a trade-off. One way that potentially you can see this is a potentially really this set of tools is a sort of a first step, where maybe you can have on average, like they can guarantee you to have a good behavior in terms of performance of your network. And in the moment you spot something, you need to switch it to something that is a little bit more accurate in some sense.
Right, so we need a third dimension in that 3D axis.
Yeah, that's correct. I think that's, guess you're talking about this. Yeah. So yeah, that's correct, actually. I think a third dimension would be, and potentially, something that will help you also to try to understand how to switch from, let's say, something that works in a common case scenario but gives you good performance, and something that is more accurate. I think in some sense, this goes into the direction of some work that I really shortly mentioned at the end of the talk on runtime programmable switches, right? So in the sense that whenever you figure it out that something is happening and something that it might be, but you need more or better monitoring tools, or tools that provides you a different set of queries, then the possibility to install is as well, and then go ahead with this new set of tools.
So Gianni, we are almost at time, and we should wrap up. But I want to sneak in one last question of my own. So this is great technical work, but I have a high level question of why are we doing this, right? So the path tracing that you showed, there's a lot of really cool insight here, but I can also do a path trace using traceroute, and it's going to work, right? And it's going to find the common case behavior. So like, why go through all this effort of like RDMA stuff into a collector's memory and making things super efficient? What does this buy us over more targeted tools? It seems like it will produce a lot of data that contains a bunch of information, but why would I deploy this, I guess, in my data center? What do I get from this that I can't get from other tools?
So in the context of these, since we discussed a little bit for the RDMA, I think the main motivation was here to try to reduce as much as possible cores and CPU for collectors.
But that's assuming that I already want to do in network telemetry, right? Why would I do a network telemetry as opposed to selectively trace routing things, or doing something that's a lot less heavyweight in terms of how much data it generates?
This is a good question. So the way that I do see that is effectively like later. One thing is like a path tracing, and for that I do agree with you. But there are like a lot of other dimensions that operators, like for example, in the context of since it's here on the slide is Alibaba, they care of multiple different dimensions along the time, which is for example, they are looking into packet drops, or they are looking into how those evolves over the time, or they're looking to queue occupancy to have an idea of somehow microburst in the network, and then because of this. These were creating, or at least in the paper that they presented last year, they call it flow event telemetry. They recognize that all this amount of information that they want to collect, it was already too expensive for collector, and so they started designing, let's say, filtering technique at the switch to try to let's say, reduce a little bit this, because yet, it's, yes, path is one thing, but there are like also multiple dimensions. But even if you consider that a scale, we realize that effectively this is potentially can burn a lot of cores and CPU that potentially, if you try to be like a little bit more, let's say, to try to think a little bit out of the box, maybe using RDMA, you can find ways.
No, I get that there's a challenge.
Yeah.
I was just curious of why would you collect so much data
Yeah.
to begin with, but I get the sense. So I think we should wrap it up here in the room. We can leave the call open if there's any other questions from folks that are online. Or people in the room, feel free to continue with Gianni. But thank you, and
thank you very much. Thank you very much.